Hi guys, this is my first video on section 9.1 and it will be about the margin of error. Now, the whole reason we've been studying statistics is because we study a sample in order to learn something about the population. But we know that the sample proportion is not going to be exactly the same as the population proportion. We know that the sample proportion is unbiased, so it will come close to the population proportion, and the bigger n is, the closer it will come. But we also know that it's not the same due to sampling error. So obviously the question is, how close is it? So we have here a sample proportion, and it's close. So somewhere in this window around the sample proportion, there's going to be the true proportion. It might be below the sample proportion. It might be above the sample proportion. That we don't know, but it's going to be somewhere in this window, and it could be round about here, it could be quite close, or it could be further away. Now, the distance from the sample proportion that we think the true proportion is, this distance is called the margin of error. And it could be this distance above the sample proportion, or it could be this distance below the sample proportion. And this entire window from one margin of error below the sample proportion to one margin of error above the sample proportion, this is called a confidence interval. I misspelled that. Confidence interval. Because we have some level of confidence no guarantee, I'm afraid, not in the land of probability, but we have some confidence that the true proportion, the population proportion, is somewhere in this window. Is in this window. And so we can describe the confidence interval one of two ways. The confidence interval, we can think of it as the sample proportion plus the margin of error on down to the sample proportion minus the margin of error. So this notation said out loud is the sample proportion plus or minus the margin of error. Or we can think of it as this window that begins with the sample proportion minus the margin of error on up to the sample proportion plus the margin of error. So the next most obvious question is, how are we going to compute the margin of error? And in order to do that, we're going to need the sampling distribution of sample proportions. So that's why we talked about all of this. I'm going back to section 8.2, and in that section we learned the central limit theorem for sample proportions if 1, the sample was SRS, 2, NPQ, PQ was greater than or equal to 10, and 3, if the sample size was less than 5% of the population, then sample proportions are normally distributed, which is why I did that bell curve there to the left. And the mean of the sample proportions is the population proportion, and the standard deviation of the sample proportions is the, that would be the square root of PQ over N. Okie dokie. So also we know about normal distributions. Here's the mean, and here's the fact that it's all the sample proportions. We know about normal proportions, normal distributions, as if it's normal, 95% of all the p-value sample proportions will be what we used to say within 2 standard deviations of the mean. But we have learned since then, as a matter of fact, in chapter 7.2, that it's not actually 2 standard deviations. That was fudging. Really, it was, allow me to erase this, after we put a little bit of time and effort into computing it, it was 1.96 standard deviations of the mean. And so 95% of all p-hats are in this window. The mean, which is p, minus 1.96 of the standard deviation, which is pq over n, on up to the mean, which is p, plus 1.96 standard deviations, which is pq over n. So that's a window that contains the sample proportion, not exactly what we were looking for. Hang on, let me clear the screen. Okay, while the video was paused, I took the opportunity to write that interval up a little bit more cleanly up at the top of the screen. So here's what I'm talking about here. Say this is all of my possible p-hats. I know that in the middle, here's this p, and if I go down, 1.96 standard deviations, and if I go up 1.96 standard deviations, I'll end up at this point, or this point, meaning that the maximum distance, I don't know where p hat is. It's somewhere in here. Maybe it's here, maybe it's here, maybe it's here, maybe it's actually quite close to here. But what these boundaries are telling me, this is the maximum distance. P hat is from the mean, which is the population proportion, is 1.96 times the standard deviation, p square root of pq divided by n. Well, let's look at this the other way. Again, this number line is going to be all of the possible sample proportions. I will put the sample proportion in the middle this time, and I will go out that maximum distance again. Because the maximum distance that p is from p hat is the same distance, the same maximum distance that p hat is from p. So the window around p hat that 95% of the time contains p is going to be that same distance, 1.96 square root of pq over n. So that is our margin of error. Or at least 95% of the time it's our margin of error. So that 95% is what we call our confidence level. So we are 95% confident, not 100% confident. To be 100% confident, I'm 100% confident it's somewhere between 0% and 100%. You may notice that's not very helpful, but we are 95% confident that the true mean is within 1.96 square root of pq over n. Now, you may have noticed a problem here. I don't know p. I know p hat, but I'm trying to find p. That's the whole purpose of the exercise. Well, here's the good news. We know, because p hat is unbiased, that p hat approaches p. Let's say that out loud. The sample proportion is close to the population proportion. How close, I don't know, but I do know that it is close. And so we're going to use that fact to enable us to do a spot of fudging here. Hold on. Here's our 100% genuine margin of error. The margin of error is equal to 1.96. That's if we want a 95% confidence level. The square root of PQ over N. But because P is close to P hat, this is very, very close to, and we'll go with close enough, the square root of P hat divided by Q, times Q hat divided by N. Okay, what's Q hat? Any guesses here? If if Q is equal to 1 minus P, what do you think Q hat might be? It's 1 minus P hat. It's the complement of the sample proportion is what that's going to be. So the way I think of this is P and Q are buddies and they dress the same. P hat and Q hat are buddies and they're both wearing their cute little hats there. So that's our margin of error. Margin of error. Hang on, wasn't it only 1.96 if I wanted 95% confidence? Okay, it's actually going to be the margin of error equals the critical value times P hat, Q hat divided by N. And what is that critical value? Well, we talked about it in section 7.2, but let's talk about it again in the next video. So I'll see you in the next video.